So welcome back. Now we have a practical part, and we will alternate. Then there will be the relational algebra, which is theoretical again. Then there will be SQL to implement it. So we are theoretical. So we now know what a relation or relational table is. I already asked you the questions. We saw that a collection is a set of records that mathematically are maps from strings to values. We know that we need additional constraints because otherwise that would be a collection too. We know that these are the three constraints we want to add. The first one is the relational integrity that requires that everything has the same attributes. Otherwise, it's broken like this. This is not okay. So this would be the kind of, if I try to draw it as some sort of things that looks like a table, that would be the actual tuples that you have in here. That don't have the same support. The second rule is the atomic integrity, which we also call first normal form because there will be a second, a third, and so on later. This is forbidden for atomic integrity. We cannot have these nested tables. And the third one is the domain integrity, where I add my domain values like this. And in that case, we don't have it. I'm not able to add this yellow line in there because, for example, true, -1, false, it's not all the same types. All right. So we saw last week what a relation is that can connect multiple to multiple. We also what a map is that can connect or not connect the elements of the left. Function means everything has to be associated with something on the right. This is why there's no cross for this one, and there is a cross for this one that says that you don't have to connect them all. Then we saw that in the textbooks, we define a relational table as a Cartesian product, a subset of the Cartesian product over the domains, or relation over the domains. We saw that by definition, that gives you relational integrity and that gives you domain integrity, but it doesn't give you atomic integrity. For that, you have to additionally request that the domains only have atomic values. Then we saw the second definition as a set of records. We saw that we need to add additional restrictions on top, but this is great because for big data, we just drop these restrictions. So technically, this is big data ready, right? I can just also have collections that are not relational tables. All right, but this is for the next semester. So a relational table would be a set of maps in that sense. I can have bags of maps that also fulfill these three, and lists of maps that also fulfills these three constraints. All right. I keep repeating things, but there is nothing better than that. If you keep repeating, spaced repetition, this is how you remember things, right? It never hurts to repeat. All right, now, SQL. It all dates back to the 70s, really. And there are these two people, Don Chamberlain and Raymond Boyce, who co-invented that language. And back then, it was called SQL, SEQUEL, because that meant Structured English Query Language. They already had a first customer that still exists today. I think I saw them in the news recently, Pratt & Whitney. And it was all done in San Jose, in California, in the what is known now as the Almaden laboratory of IBM. And the name of the system was System R. R, of course, you might guess why R, it's relational, right? Okay. But then they had a trademark issue. Some people were not happy that they called that SQL like this because it was already taken. So they needed to find another solution. And this is why it's called SQL now. And in fact, that's the reason why now half of the people say SQL and half of the people say SQL, but it's really the same thing. It's really only a matter of pronunciation. Technically, the people that have been either in the first ones to deal with databases or that have been influenced by these, they tend to say SQL. And I think the general public says SQL a lot. All right. And that language, as we will see, is declarative, it is functional, and it is set-based. Declarative is very good news for you because it means it's very easy to learn. Contrary to a language like Python or Java or C++, where you would have to put a lot of effort telling the computer what to do and writing for loops and so on, can get very long, SQL can be very concise. You can say in just a few lines something very powerful, and PostgreSQL will take care of executing that for you. It's declarative. So this is really like Imperative would be you cook yourself. You go buy the ingredients at the grocery store and then cook. And declarative would mean that you go to the Mensa and ask for a menu, right? So that would be the declarative version. And you delegate the cooking basically to the Polymensa team. Set-based means that you don't manipulate single values, but entire tables at a time. It means like huge sets can be millions or even billions of records at the same time. So this is why we call it set-based. All right. So now I will dive, because that's what we need in order to go into PostgreSQL. If you want to create your first tables in PostgreSQL, you will have to say what attributes you have, and you will have to say what domains you have. So we'll first go through the menu of domains. Let's look at all the domains we can have, and then I'll show you the syntax in SQL to create tables that have these domains, right? So the goal is really to define in SQL a schema like that, where you specify the name of a table, the name of the attributes, and the domains. There are plenty of kinds of domains. The good news is that it's pretty standard in the sense that whatever product you use is going to be more or less the same thing. But I'm only saying more or less because there can be small details that change, right? It might be that some of the products will not have some domains, and some others will have extra domains, right? And the names might also vary. But I don't think this is complicated to understand, because we are in Switzerland and there are as many dialects of Swiss German as villages, and it's kind of the same thing for the products, right? There is SQL, like high SQL, if we call it this way, like high German. And then we have like Zürichdeutsch, Baseldeutsch, or Schweizerdeutsch, and so on. But then you have PostgreSQL SQL, you have IBM SQL, you have Microsoft SQL Server SQL, and so on. You just need to be prepared for some differences. But if you forget about the small differences, we all understand each other in Switzerland in spite of the different dialects, and we each talk our own. But in the end, this is all the same thing we are talking about. So let's start with strings. And again, here, some of you might already be familiar with this. Some others might not have been exposed as much to programming, so it might sound trivial. But a string is just a sequence of characters, right? In that case, the first case, FOO, then ZURICH. That's what it is. We typically put them in double quotes. That's kind of the popular thing to do in computer science, so that we know that it's actually meant as a string. Single quotes might also be found at some places, right? So this is what a string is. If you want to sound fancy, it's technically a monoid. That's what the mathematicians call the strings. It's a monoid that has a concatenation operator. It has a neutral element that is the empty string, right? If you concatenate the empty string, it doesn't change anything. So you wouldn't imagine all of the theorems you can prove on these things. But for us, we don't care. We just want to store these as values in our tables. But the cool things that we can do is a few constraints. For example, imagine that you want to store car identifiers, like the control shields of the cars. Then technically, that's a string with two characters, like ZH for Zurich, AG for Aargau, and so on, right? So you have the possibility in your table to restrict, to say, I want a string that has exactly two characters. That would be an example for the Swiss cantons. Now, if you want to go international, you might not want an exact number of characters, but you can also say at most 3 or at most 4, and that gives you this kind of feature, right? You just give a maximum, but it can be less. And here you see with the countries like FD, like France and Germany, they have just 1 letter. And then the United Kingdom and Switzerland, they have 2. Ireland, they have 3, and so on and so on. You can also do this. And something that happened a bit more recently, because back then it was really tougher to do and not recommended. Now we can even add strings in our tables that don't have any limits. They can be as long as you want. Technically, it could have been a problem before if, imagine in your relational table, you are hosting some sort of WordPress server for your blog, and you want to store your blog posts in there. The blog posts, they don't have any particular limit, right? So you want to be able to do that. In the past, we didn't use that without limit. We typically set one of the traditional things was 255 as the limit, but of course, some people might not find this enough, but that's technically the idea. So we have these 3 things we can do. We can require a fixed length, we can cap the length, or we can not set a limit. And now, and I'll do it every time, I'm giving you the names written in this console font. Don't be scared, I warned you, it's like Swiss German. There might be plenty of different ways of calling them, but it's really the same, and there's all sorts of synonyms. If you want a fixed length, then you just say character 10. You can also say char 10 if you want to, if you're too lazy to write the whole thing, it's the same. And just char would be just 1. Then you have character varying that puts a cap of 10, but it can be less than 10. And varchar is just the abbreviation of character varying. In fact, most people use varchar. They don't bother to write character varying completely. So that's the second kind that you can do. And then we have without limits. Text and varchar, they are non-standard. If you say varchar without any number, that's technically without limit. Text is another one. Club, does anybody know what club means? That means character large objects, if I'm correct. So this is technically just some funny way of abbreviating it. It just means you have a very long string, and you allow some very long strings in there. It's called a club. All right? So this is it, and this you can use in PostgreSQL. Yes, maybe we can actually use the microphone, because otherwise I have to read it right here. Go ahead.
Okay, actually 2 things. First, I wanted to ask what the non-standard means. And the second, I wanted to apologize. I downloaded the week 2 things a while ago, and I must have gotten confused because I changed to week 3.
Oh, now it works.
Yeah, I'm not sure.
Yeah, all right. But I'll check anyway that it's all up to date and that it's all uploaded, right? Let me answer your first question too. Non-standard means it's like this High German and then Zurich, Baseldeutsch, and so on. So technically, there is a SQL standard that exists. It's very long. But the implementations, they don't exactly implement the standard. It would be nice, right, if everybody implemented the standard, but this is not how it works. In fact, the standards, they appear in the other direction. It's like you have like 10 or 20 companies that build their own products that are not quite the same. Then they start realizing the value of interoperability, and it would be nice if they could kind of agree on as many things as possible. So what happens is that there is some sort of standardization committee that is created, a working group, and then every company sends representatives there, and then they sit for a couple of hours every week for a couple of years. And then at the end, they have this fancy document that gives the standard, and then it's best effort, right? They all try to, modify their product in order to get closer to the standard. So it's really a collaborative effort of the companies. And so what I mean here is that text and varchar are technically specific to PostgreSQL, but I don't think it's in the SQL standards. That would be club that you would find in there. That's what is meant. But just so you know, in this course, we really focus on PostgreSQL. This is the focus we have. This is kind of the SQL dialect that we are going to learn. So you really just need to learn whatever applies to PostgreSQL for the sake of the course. I won't expect you to know what is standard, non-standard, and so on, just PostgreSQL. In fact, the reason I pick PostgreSQL, and a lot of my colleagues who are teaching databases, they pick it as well, is that it's one of the closest to the standards. MySQL, some people use MySQL. MySQL is one of the farthest to the standard. So it has a lot of things that really differ from the other products, but PostgreSQL really is close to the standard. But technically, at the end of the lecture, once you have learned how to use PostgreSQL, it will be very easy for you to use any one of the others, even MySQL. The only thing you'll need to do is read the documentation. You'll have to look up things like, oh, I'm trying to put text, but it's not accepted. So just open the documentation, find the types, and then you will see they will have something equivalent to it, right? So it's just that you will have to use the documentation, but the rest, all the understanding of how things work, it's really there, and that will make your life very easy, right? Okay, did I answer your question? Okay. Now, I'm also going to give you a few details on the behavior, because what happens is that if you have exactly 3 characters, what happens if you have less? Well, it's going to add spaces. So if you put an empty string and you say char3, you're going to have 3 spaces in there. If you have just 1, it's adding 2 spaces. So that's called padding, right? You pad until 3. You throw an error, of course, if there are more than 3 in that case. And you can also cut, if there are extra spaces, you just remove them, right? And then this is also the correspondence with the varchar that is a cap. So you don't add spaces, of course, but you would reject if it's more than 5. And of course, if it's unlimited, then you just take the string as it is, right? In general, the recommendation and what many people do is to use varchar with some number. So not the unlimited one, not the fixed one. Varchar 255 is actually quite common. Right? Char n eats up a bit more space because it has these spaces in there, right? So you have to be careful, even though it might be optimized by more recent engines. All right, that's the strings. Now, the integers. So mathematically, integers are basically the set Z, which is a ring with addition and multiplication. And we can actually use addition and multiplication in the SQL language, which is really nice. But what's important to understand about all of these types, and this is true not just for integers, but also for dates, like all the other types we will see, is that you need to distinguish between the actual value space, that is that are the actual values, and the way you write it on a piece of paper, the representation. For example, for an integer, that would be the representation in base 10, right? So if you have the 4, you will write it as 4. 42, you will write it as a 4 and a 2, right? But that's only a representation. And in fact, that representation, if you think of it, that's just a string, right? It's a 4 and a 2, so that's a string. That's called the lexical value of your value. It's the lexical space. But when you start reasoning with it and doing math or operations on it, like addition, multiplication, of course, you're not using the string for 2, right? You're using the actual 42ness, if I can call it that way, of the number, and that's your value space. So the value space, that's really Z is the value space in the case of the integers, right? And the lexical space would just be the set of all the representations in base 10 or even in other bases of these values, right? So you just need to be aware of that. Do not confuse the way it appears on your screen with the actual abstract value that you mean, right? This is another example. So here we have 4. So there's the actual 4, the mathematical number, and then there's all the representations it can have on the right. B means Boolean, so 100 would be base 2 and so on. All right. Now, if you already programmed, you might already have encountered some of the integer types. And this 4 in particular, this is Java. There's byte, short, int, long. Who has already seen something like that? Who never saw something like that? Almost all of you, perfect. So this is just a restriction on the interval, right? If you have byte, for example, you only allow the integers between minus 127 and plus 100 and, no, I'm getting it wrong, minus 128 all the way to plus 127, if I'm correct. And that's 256 in total. And 2 to the power of 8 is 256. So this is byte. Short, it's the same, but it goes all the way to 65,000 something. 32 goes all the way to 4 billion something. And long goes all the way to something like 16 quintillions, I think. So that's a lot. The long. But technically, this is because in the end, these integers, they are stored on a computer. And in a computer, if you have a fixed number of bits, it's much more efficient to store. They also exist in SQL databases, so you can actually, and not named that way, of course, but you can also do this. Don't overestimate the design. I can give you a concrete example. On YouTube, back then, I would say maybe when it was invented at the end of the 2000s, maybe around 2010, the counter for the number of views on a YouTube video was an int 32 bits. Because 4 billion will never reach 4 billions, right? Actually, we did. And that was the Gangnam Style video. You remember that one, Gangnam Style? It actually broke the counter. That basically brought them back to the negative numbers and so on. And that forced actually the YouTube team to change that to long, 64 bits. All right. Okay, so this is it. You have the exact intervals in there. You see it's even negative, positive. And this is how they are called in PostgreSQL. Small ints, that's for the 16-bit integers. You have integer and int. They are both synonyms for 32 bits. And big int for longs, right? 64 bits. In practice, I mean, now we tend to use long a lot, like the the 64-bit integers are usually, especially if you do big data, that's what you need. Now I'm waiting for the day where we have more than 16 quintillion records. That might actually happen someday. All right. And then you have so you need to understand that there is this binary system, right? We can write in base 10, but we can also, it's only a convention because of the number of fingers we have, but we could have done it in other bases, right? Now, this way of storing integers, it's very popular, it's very nice, but sometimes it's not enough because first you need decimals with a decimal period. And second, you might need arbitrary precision. Imagine that this precision with for the quintillions here, these numbers, that it's not good enough, the precision. Imagine your CERN, you're running physics experiments and you want 30 decimals after the comma. I don't know if that actually still means something, but just to give you an idea. So what if you want this precision to be arbitrary? Well, technically, the mathematicians have a set for that. It's called D. That's the set of decimal numbers. It's the set of all numbers that have a finite representation in base 10 in digits. And the total number of digits on both sides of the decimal period, that's called the precision. That is 32, and you can cap the precision in your type. And then we have what's called the scale. That's the number of digits after the decimal periods, precision and scale. So if I want to put a cap on precision and scale, I can define types like that, right? So if I don't want any cap, that's just called numeric and decimal. I can put anything I want in there. Of course, when I say anything, there's always the physical limits of the computer, right? But technically, there is no documented restriction. Then you can limit the precision and force a scale of 0. That means we have an integer, right? If we have nothing after the digits, 0. So here I allow for 32 digits. That's numeric 32, this capacity, for example. And you can also limit both the precision and the scale. In that case, you have 32 in total, and it means 22 after the decimal period. And if you have all the 22, that would be 10 before the decimal period, right? That's it. And now you can experiment. I'm not entirely sure because, of course, I don't know everything by heart. I'm a human being like you. But basically, if you try to squeeze these numbers in there, that's more or less what you would get with these 3 different types, right? Numeric, which is anything. Numeric 3 that has a precision that is capped to 3. And numeric 3 that is integers with 3 digits. And numeric 3 would mean that you accept 1 digit after the comma, right? So that's the behavior. Should we have a break? All right, let's have a break. I'm giving you 1 minute. So let's take a break and go back in 15 minutes here, and then I'll continue with the digits, right?